by u has basis vj plus u such that j equals 1 to ... n minus k. Now, to prove that that's a basis, what do you need to do?
Sure, it's linear independent and it expands.
Yeah, linear independence and spanning, exactly. So check this out. If x is equal to, a sum over, let's say, ci ui, I equals 1 to k, plus the sum over bj vj, sum j equals 1 to n minus k, right? If that's an element of V, right? Then, x plus u, I may not be putting my ducks in a row quite right, but what I'm trying to say is if you take an arbitrary element of the quotient space, namely x plus u, right? Then x, being a vector in V, has a unique decomposition with respect to the basis beta so constructed. In particular, it's got a piece in here and it's got a piece in there. But then you can see that this is going to be equal to, we can throw away, right? We can throw away the part with the c's. Why can we do that?
They all map to, they're the zero.
Right. Well, they're elements of U. So let's think about this logically. If I take, let me give this thing a name. Let me call this thing Pac-Man, right? So notice that, let me call this thing Ghost. So we've got x is equal to, Pac-Man plus Ghost, right? But I guess what I'm trying to tell you is that Pac-Man is equal to x minus rats. It's immediate from the lemma we just proved. I need to think about it the right way. My claim, let me write it a different, let me say it a different way. Let's think of, so that's x, right? And this is quote unquote y. What's y minus x? What's y minus x? So if I take this and I subtract x off, or maybe I should do x minus y is more natural. X minus y. So if I take, this is all x, right? I subtract off that piece, I'm left with that's an element of U. So the difference of x and y is in the subspace, which means that that's the same coset. All right, great. But this, by the definition of addition in the quotient space, is the sum j equals 1 to n minus k of b sub j times parentheses vj plus u. So this proves that that right here is a spanning set for the quotient space. Do you see it?
Are we?
So right here, this is a vector in there. This is a linear combination.
Okay.
That's an arbitrary element of the quotient space. It can be formed as a linear combination of these vectors.
Yeah.
So you don't need the u's. The u plus u's. Those are, I mean the, in my notation, the u plus u's are irrelevant. Now then the question remains, why are those linearly independent? Can we prove linear independence of this? So if we have the sum over, let's say, bj, vj plus u, right, equals to 0 for j equals 1 to n minus k, our goal is to do what? Is to prove that the, oh, quiet, what's that? Oh, Wayfair. Stupid Wayfair. I bought some barn doors from Wayfair. They've been harassing me ever since. What's that?
We're trying to show that all the BJs are 0.
All the BJs are 0, that's right. So this, this means that the sum of bj vj, right, j equals 1 to n minus k, that thing plus u is equal to 0. But keep in mind that 0 is really 0 plus u here, right? That's the 0. That is the 0 of the quotient space. So what this then means is that the sum is an element of u. But that forces that to be 0. If it was non-zero, then you would have a linear combination. Then you'd be able to write part of this base, part of that basis as a linear combination to the other basis. It would contradict the linear independence of our basis constructed when you get through the details. So this implies that the sum, and admittedly there's probably a paragraph to write there, but essentially that's it. So this j vj is equal to 0 by linear independence of beta and the construction of the v's. But then, because it's a basis, because these are constructed to be linearly independent, that implies that the b1 so let's put it all together. What did we learn about the dimension? So all of this shows that the dimension of the quotient space of v by u is equal to n minus k. What is k? What is n? N is the dimension of v. K is the dimension of u. So there we go. The dimension of the quotient space is the difference of the dimension of the total space and by the space which you're dividing. So for example, if you have a function on 3 dimensions and the kernel is 2 dimensions, then when you take the quotient by the kernel, you're left with a 1-dimensional space. All right? So next time, because I guess we're out of time for now, but next time I will talk to you about more. I've thrown this out here, but this begs a deeper discussion, right? We should talk about what it takes for a vector space to be the direct decomposition of its subspaces. That's really the last remaining subtopic in that chapter. And I mean, it's nice to do an explicit example with this stuff to like kind of flesh out the idea I had over here. But so maybe if the mood strikes me, perhaps I'll actually put this, elevate to an isomorphism into practice, right? Because that's the first isomorphism theorem is also what we're coming up against, right? The first isomorphism theorem says what? If you take the mapping you mod by the kernel of T, which this is a quotient vector space, right? Then that's isomorphic to the image, right? That's the first isomorphism theorem, which is different than the first isomorphism theorem you've seen in abstract algebra. Because in abstract algebra, typically in group theory, we're talking about well, you might see it in the ring theory and in the group theory, depending on how things go in a semester. But for groups, you take a group mod by the kernel of a homomorphism. Well, it's isomorphic to the image of the homomorphism, right? And that makes sense because we proved the kernel is a normal subgroup. And then in the context of ring, you take a ring, mod the kernel of the ring homomorphism. That's automatically normal because the ring addition is abelian, and abelian subgroups are automatically normal. So like when we talk about factor rings, that is an easier thing to do. Vector groups come with strings. Like, you got to divide by the right kind of group. You can't just divide by any old group. You have to divide by a normal group. But for a factor ring, you can divide by any subring. And there, of course, there's an isomorphism theorem there. There's also a second and a third isomorphism theorem, which involve like quotients of quotients. And there's a fourth isomorphism theorem called the lattice isomorphism theorem, which actually involves seeing relationships between a lattice diagram. My brother says everything can be proved with the lattice isomorphism theorem if you're willing to do it. But anyway, we'll stop here. So next time I want to show you about decomposing a given vector space as a direct sum of subspaces and what that does for the matrix. That brings us to like the block diagonal matrices. And in that sense, eigenvectors are a natural next thing to talk about. But instead, we're going to talk about geometry, which is the next chapter. So we'll follow that, yeah. And hopefully, we'll actually have Monday to work with next week, so we can get a proper amount of algebra in our week. Yeah.